All right, hello there. We'll be getting started in just a minute here. Okay, I think we're going to get started. So, thanks for tuning in. We're still making do with this strange remote talk we're having to do, but hopefully it's been good so far and will continue to be good. This week, we're going to be having a look at program obfuscation. In a nutshell, obfuscation is how you protect a program from being understood. Uh, it's a pretty wide variety of ideas here. A lot of kind of hard computer science theory and a lot of squishier theory. So, with that, let's begin. So, first off, we're going to have a little bit of background here. So, back in the spring, oh, sorry, back in the fall, I should say, you probably remember that we had some talks about pwning, some talks about, cryptography, and we talked about reverse engineering. So to reverse engineer a program is to figure out what it does. And there's a whole lot of ways to do this. You got, your big disassemblers and decompilers, IDA, Ghidra, Binary Ninja. You have debuggers like a GDB. You've got things like objump and strace and ltrace for, seeing what's inside a binary and what kind of stuff it's doing. And there's also R2. Someone uses it. So we kind of break reverse engineering down into two separate categories here. We have static analysis and very loud. Let me turn it down a little bit. Yeah, so we have static analysis and dynamic analysis. Static analysis is something where you are just looking at the program as is, not running it. It's quite useful for understanding what a program looks like, but it isn't generally as comprehensive as dynamic analysis, where you actually run the program until you can make sense of what's going on. Of course, the challenge with dynamic analysis is that there can be, an incredible number of ways a program actually executes, and finding them all is challenging, to say the least. But both of these are very useful for figuring out what a program does, what secrets it has, who wrote it, all kinds of things. Now, we're just going to briefly talk about some things you've probably already seen. So, the easiest situation is when we have debugging symbols. The debug symbols tell us, things like source lines and label everything nicely. They make debugging a lot nicer. So if I go into GDB, you don't see too much in a disassembler, but if we pop into GDB, we can see source lines. We can see, all sorts of nice stuff. This makes it a lot easier to figure out what on earth is going on. Because as you know, decompilation is hard, so we'd rather not do it. So this is how we might debug or even reverse engineer your own code. We usually don't have that, though. So if you compile a program completely normally, you're going to get something like this. So we can see the assembly pretty clearly, and a smart assembler can also tell us things like, oh, there's hello world, and so forth. Uh, but we might not necessarily get all the details. But you can see here, like, oh, okay, hello world, calls, puts. It's pretty clear. And unfortunately, in a debugger, we can no longer get our nice source lines. So, a bit of a loss. But you can still figure out what's going on here. And yeah, and so like, we can still find main. So it's pretty good. Now, when you're doing CTF challenges, most of the time you're going to get stripped binaries. There's a program called strip that does that, and what it does is it throws out a lot of stuff that isn't strictly necessary for making a program work. It's going to be a lot more annoying to work with, but it'll still execute. And so if we go to GDB and now say, okay, break main, there is no main function. That's a bit of a bother. Now we can still track it down. Again, Binary Ninja here has figured it out quite handily, but you'll just have less to work with. Now, all this is stuff we probably already heard of. But that's the kind of the basic stuff that will be making infinitely harder in short order. So reverse engineering might be fun, but there are problems. So, for example, software pirates would love to reverse engineer your game to figure out how to, crack the game, make free copies. And maybe they want to make aimbots for things like Assault Cube, but I know no one here would do that, so we'll move on. And then more kind of in the corporate world, you might be worried about intellectual property. If you have some secret technique that you really don't want your competitors to know about, you don't want them to find that out. And so these are all bad for some definition of badness. So that raises the question, how do we stop this? How do we fix this reverse engineering? The answer is simple. Litigation. So all you do is get a lot of money and then beat everyone you don't like with the money until they go away. And this is how Oracle has operated for decades. It's fantastic. Unfortunately, not every one of us works at Oracle. Some of us are not vampires. So, what do we do instead? Like, maybe we can offer our software as a service. If no one can actually see your program, then they cannot do anything with it. They can't steal it. They can't, they can't even look at it. That's what we call it, a black box. Because you put some data in, you get the data out, you don't know what's going on. You can also ask really nicely, but this generally does not work in practice. And then another thing we can do is obfuscate. So obfuscation at a high level is hiding what a program does. It could be you're trying to stop somebody from seeing that this is actually a ransomware, or maybe you're just trying to stop them from patching out your license checks in Sublime Text. But it's a little bit hard to define and to quantify. It's kind of like saying, how hard is this puzzle? You can kind of make these rough classes of difficulty, but like you can think about it, any maze is trivially solvable by a computer that just solves mazes. But for a human, it might be almost impossible. So we've tried to kind of quantify this. It's like, okay, maybe obfuscation is the program is this big or it's this complicated, but it's difficult. So the holy grail of all of this is what we call like black box obfuscation or virtual black box property. Ideally, it would mean that the program is no better than having access to an oracle that runs the program for you. It never shows you the program. Unfortunately, this is impossible. There's actually a negative result for this. You cannot do this in all cases. So it's kind of like the halting problem. Just can't do it. Sad. And the theory is rather complicated. I've read through a number of these papers, and I'm not ready to explain them to anyone else yet. But it is an interesting read. We'll have citations at the end, by the way, if you want to check out any of these sources. So, we can't have the Holy Grail, but we can have what I call the regular Grail, pain in the ass obfuscation. Basically, if it's a pain in the ass to reverse engineer, it's good. So that's our metric here. If I don't like it, it's good. It's a little bit strange sounding, but I think it's a nice metric. So we want to make it so that it is, one, hard for somebody to understand the program. That is, this obfuscation is potent. Two, we want to stop somebody from getting rid of the obfuscation. That means the obfuscation is resilient. And three, we want to keep it efficient. We don't want the program to take 20 years to run to print out hello world. That's efficiency. So these three kind of key metrics were laid out way back in 1997 by Kohlberg, who we'll get back to at the end of this presentation. He's still hard at work here. There's also stealth, where we try to keep the obfuscation from being visible, but that's even more subjective than usual, so we'll be passing on that. So that's the kind of gist of what we want. We want to make it so that the program is hard to understand, hard to make it easy to understand, and still works well. And just as a preamble, most of the examples I'll be showing here are generated by Tigress, which is an excellent obfuscation framework, which we'll be talking more about at the end. Screenshots are going to be from Binary Ninja, shout out there. And most of the figures are from various academic publications, because making figures is hard, and everything is terrible. Let's get started. So, in a normal program, you use call to invoke a function. You use ret to return from a function. All this makes sense. You maybe use jump to make an unconditional branch. Now, a spicy program does not do this. So, for example, instead of using jump address, you can do push address and then sometime later call ret. This has the same effect as calling jump. The stack is the same. The program is running just as usual. Unfortunately, reverse engineering software might not see it the same way. Similarly, the second one also just does a jump. All we do is we push the address, we call into a function, and then we just return again. And as we see here, this winds up just hitting a ret instantly and going back to that address. So this kind of stuff is confusing. It violates all the rules. We're using return to do things that aren't returning. We're using call to go to places that aren't functions. And we have rets that don't end a function. So one of the main strategies used to actually disassemble a program is to just follow all the calls. And it's kind of this recursive descent. And this is monstrously complicated by this kind of weird control flow. Because all of a sudden, you don't have these guarantees. And speaking of things that are not as they seem, we're probably all familiar with basic blocks. Basic blocks are a sequence of instructions that you go from the start to the end, and then at the end of the block, there's some kind of condition or some kind of jump. So it might be a couple, some arithmetic and some stuff, and then it'll have a comparison, and it'll jump to two different places. Now, a fundamental thing you'd expect is that basic blocks are separate. They shouldn't overlap with each other. Unfortunately, they do. So here we have a example of how one stretch of memory can actually be three completely separate instructions, depending on where you jump into it. You can see here we got some move, some setto. There's some weird stuff going on here. We do an or and then we jump somewhere. But if we jump right here, we're going to get something completely different. We're going to just jump to that address. And if we go here, we jump to a different address. So this happens because x86 has multi-byte instruction and more importantly, variable size instructions. As Glenn can attest, you can have instructions that are dozens of bytes large and do nothing but a number. So this can result in kind of these weird polyglot stretches of memory. And reverse engineering tools, once again, can have a lot of trouble here. They can make assumptions that just do not hold up in practice. So yeah, this is going to cause a lot of confusion, especially if your disassembler is just walking from the start to the end. If it just walks through the program linearly and disassembles everything, if it's at the wrong offset, it's going to miss this. But of course, if we use a recursive analysis system, then we're going to get confused by call stack manipulation. So there's no golden bullet here. Like, there's always something that can throw you off. So that's kind of weird overlapping stuff and interpreting the program 3 different ways. But now we can get on to some, I think, some more meaty stuff. So a predicate is a condition. Pretty straightforward. If x is less than 3, if true, while the sum of is bad. We could obfuscate our program by adding predicates that only ever go to one side. If true, destroy computer. Else, don't destroy computer. If you didn't do any kind of reasoning about what these branches are doing, you'd think, okay, so maybe it could blow the computer up or it could not blow the computer up. And then maybe you have if true, a legal instruction, which would crash your program. So this can really confuse static analysis. You get these wild goose chases into these swamps of code you never actually execute, or maybe illegal instructions, or maybe you just have 30 layers of nested if-elses, which will cause a symbolic execution program to grind to a halt as it tries to consider all 2 to the 30 paths. However, these are pretty obvious. Like, if true, I think we can figure out which way this is going, and it is not the else branch. So this static analysis can throw out dead code, thus killing off our lovely, this branch here. We're going to throw this whole thing out, and we're left with only detonate computer. That sounds malicious. So what if we tried a little harder? Like what if we said, okay, if rand is less than 0, and that's not true, then launch the missiles. As you might know, rand always returns 0 or a positive number. So this will always happen. And then maybe we have this big global variable that everyone's poking at. And then, okay, the least the bees. Again, so these things are kind of less obvious, but you can still reason your way through them. And this is where opaque predicates come in. A predicate that's very difficult to understand and very difficult to predict. Now, the important thing is that it is easy for the creator of the predicate to understand, just not easy for somebody coming in and analyzing it later. Kohlberg et al. Have a great paper from 1997 about all kinds of ways to make these constructs. Just as a sample of that, here is one such beautiful opaque predicate. This is essentially, for anyone who's taken program analysis, this is an abuse of how hard points2 is to analyze. We have all these different graphs, and we have things moving around the graph, and we're breaking the graph up. The end result, it's very hard when you're looking at it from the outside to guess what's going to happen when you run it. But it's obviously very easy for whoever created it to figure it out. So in that dead branch, we then put illegal instructions, symbols that don't exist, slightly buggy versions of the actual branch, or nothing, whatever floats your boat. So as an example, this is the result of applying Tigress to a Hello World program. Now, this kind of thing here, this goes up really far. It's creating a large array and then manipulating it in a very unpredictable way, producing a test at the end here, this comp, which then causes a jump. And we either execute the real code, which is hello world, or we execute actual random bytes, I think. I don't know what SBB even does. And they're clearly just random garbage being shoved into the program. So if you actually ran this, it would either not work or crash. But the important thing is that this side never happens. Only this branch ever actually executes, thus making this an opaque predicate. So yeah, there's weird stuff going on here, and if you add, that was just one opaque predicate. So this is 5 opaque predicates strung together. And you see we're doing all kinds of weird tests and other such things here, and it gets really bad really quickly. This is a 100, by the way. I couldn't zoom out any further. So yeah, and all of these execute very quickly. These aren't slow or painful to actually execute. So this stuff is quite nice. So we can kind of try to defeat opaque predicates by things like taint analysis, where we track where input goes or where certain data goes. So we can say, oh, okay, so this thing does not depend on any of the program's inputs, then it's constant. Now, of course, opaque predicates can include input and random data. Tigress has options for that. Something fun. And as a result, some branches might just be too hard to rule out automatically. So you can use your best judgment. But if you're wrong, your analysis will be incorrect, so no pressure. So that was stuff that you could still theoretically kind of understand statically. But now we move on to self-modifying code. And this is code that eschews the normal principle of you're either writable or executable. Just do both. So these programs can decrypt data and then execute it. They can restructure the program as it's running. This makes analysis very obnoxious. Static analysis just sees a blob of encrypted data or just meaningless instructions. And even dynamic analysis has to keep track of all of this. If you think about it, you want to keep track of the control flow, you have to remember every state of the program. And that can get very expensive. So this is what legitimate just-in-time compilers do. For example, the Java Virtual Machine will JIT code down to native instructions. And this allows for it to optimize for its particular platform and without doing lots of compilation in advance. JITting is also used by obfuscators to produce unreadable code. And if I pop open Binary Ninja here, we'll see a nice example. So this is a JITted program. Now, the control flow graph is not what I would call good. You see it's kind of a line. It just goes down to the end. I promise this prints hello world. It did take about 3 minutes to compile, however. So if you're looking closely here, there's absolutely nothing. There's nothing visible here. It's a massive pile of instructions. And if we look for hello, let's see here. It might find. We'll come back to that later. See if it found hello. But anyway, let's go back to. Oh, I can't get out of here. That's not going to find it. Let's get back to this. So yeah, as you can see, that was a hello world program. You can fit all the source code from the original program into 10 lines. And that wasn't particularly aggressive settings either. Although I should say that this also included a whole bunch of opaque predicates, which probably inflated it a little bit. And this can be taken even further to give you polymorphic code where every execution is completely different. The outcome might be similar, but the resulting instructions are not. So you often see this in the context of malware, where it's desperate to not be detected by antivirus systems. So it's going to change what it looks like every single time it runs. Now we get on to a particularly nasty technique. So you might be familiar with virtualization in the context of, putting Ubuntu on a virtual box, but this is different. So when we virtualize a function, we create an interpreter, and we create an entire instruction set to run that function. So this is an example from the Tigress website. You can see here we have this big while loop, and it just says, okay, forever, we're going to take the program counter, and depending on what we're pointing at, which could be here or here or here, we modify the program counter in some way, and then we do something. So maybe we have a const where we just read the value from what we're looking at, or maybe there's a goto where we set the program counter. And this allows for us to create our own instruction set, possibly at random, to run a single function. And here's another example from a more recent publication, which is talking about attacking this stuff. And so you see here, this is a really simple one. It has add, move, multiply, and return. But this allows us to take this rather simple function and turn it into a mess of bytecode and a virtual machine. So now we have to analyze this weird interpreter. We've kind of abstracted ourselves away from what we're used to. And furthermore, virtualization can, of course, be nested. Now, of course, this also comes at incredible runtime cost. You think about it, we've taken what would be let's see, a total of 4 instructions, and we turned it into a rather large blob of code, and we're going to have to run through this over and over again. Big inflation of instructions there. And so if you do that twice, you're going to get massive amounts of code. So attacking this is challenging, but things like symbolic execution can help us here. Like the paper that this was taken from discussed how you could attack this by trying to work out what depends on user input, what doesn't, and then using that to actually turn all these weird instructions here into something much simpler, and then just analyzing it as usual. So it's never impossible. Again, it's impossible to prevent someone from learning anything about your program, but it is possible to make it very annoying to debug and to reverse engineer. Then one little thing here is what I kind of call de-optimizing. So again, program analysis people might be familiar with this concept of optimization. So things like constant folding, where you take 10 times 10 and you just make it into 100. All this good stuff, getting rid of dead code. So if we just do all of that in reverse, we create a larger, less efficient, more difficult to read binary. So we do things like we just turn a constant into a big pile of expressions, and then we do that every single place to the constant. We can do things like trying to push things into the kind of global space so that this function depends on lots of global variables in weird and annoying ways. It's basically just writing the program really poorly, but deliberately. And so this winds up producing very irritating programs. So that covered a variety of techniques, and there's a lot more out there. Like if we have a look at the Tigress site here, there's a fair bit of options here. We can do things like copy every single bit from argc into a separate variable to frustrate taint analysis. Or we can turn a literal into this big mess of code. Or we can take a function that has this nice control flow graph and smash it into just a big lookup table. There's a whole lot to do here, and JIT dynamic is probably the worst here. We're talking about a JIT compiled function that also modifies itself at runtime. That was used to make this completely atrocious program here. So this is a self-modifying, just-in-time compiled program with opaque predicates all over the place. Yeah. It's pretty gross. So that was kind of some theory here, but now let's go into how these things show up in the real world. So first up, binary packers. So a packer is something that takes a program and it wraps it up to do something useful. Most commonly, it's to protect it from being detected by antivirus by, for example, encrypting the program and then decrypting it at runtime. And this will make it hard to detect. It makes it a pain to reverse because you have to figure out at what moment the program is fully unpacked so you can actually analyze the thing. And particularly nasty packers will never fully unpack the program. They'll be kind of inextricably linked to the program so that they can never just be ripped out. And so they can do all kinds of things. Like you can detect the presence of analysis tools by checking timing. Like if it takes a whole millisecond to do malloc, someone's probably intercepting that call and doing something weird. So you can then say, oh, okay, I'm not a crypto ransomware program. I'm a nice normal program. You can try to hide where the program actually begins, and they can even pack other packers. You can have packers that have multiple packing stages and then unpack another packer, and so on and so forth, producing these very tangled webs of executable code. That was not the right button. And so if you're interested in this, there's a great paper, Binary Code Obfuscations and Prevalent Packer Tools. It is a fun read. For example, do you know that there's a protector called Yoda's Protector? It's apparently used mostly for legitimate programs, which is surprising. Now, speaking of malware, let's talk about DRM. So, DRM, or Digital Rights Management, as the full acronym is designed to prevent you from stealing, Doom Eternal, except for when Bethesda accidentally includes the unobfuscated version of the program for free. So that was a little bit funny. Yeah, they released a copy of the game executable without de novo on it, or without whatever their DRM system is, which is fine. So anyway, DRM has to be opaque. It should not be easy to figure out what the DRM is and what is not the DRM. Because again, just like with the packers, you want to make it so it's really hard to just pull it out of the program. It shouldn't be like the Sublime Text licensing check, which is basically this, but with a little more going on. Now, it also needs to be hard to remove because again, it shouldn't be easy to, even if you can find what the DRM is, it should be really hard to take it out without destroying the program. So yeah, it's kind of like malware, isn't it? So DRM will do all kinds of tricks that's very similar to binary packers. Things like VM Protect, which virtualizes your program or virtualizes certain important parts. Your DRM might phone home to say, oh, okay, am I still licensed here? And this can make it quite irritating to work with. There's also, things like detecting, virtual machines. So it's basically legal malware, which is a little bit funny, but soapboxing. So, I mentioned this earlier, Tigress. It's software developed by Christian Kohlberg, who is the author of that 1997 paper and continues to do work in obfuscation today. I think he's in the author list of like half the papers I cited here. And he's been working on this for a while, as a figure from the original 1997 paper shows. With all due respect, it's a very 1990s paper. So, if you go to tigress.wtf, great domain, you can grab this for yourself. The source code isn't publicly available. You have to go ask nicely for it. But you can just grab binaries. It's available for like Linux, I think Windows too. And it will turn your C code into awful C code. And as I showed earlier, it has a whole lot of these transformations. So it will produce excellent looking code like this, which is I think this is part of the is this part of the JIT or no this is virtualization. This is a single instruction in a virtual machine. This is the name of it, this whole thing, which you can strip out with strip later. And then this is like what the instruction actually does. These are very complex semantics here, which makes them very irritating to analyze. And yes, as he said, you can do if not licensed exit, but your program will then be the kind of baby's first patching example that RPSec uses. So yeah. And then over here we have a little bit of jitting. So this is the source code that a factorial function turns into. Very readable, very nice. What's going on here? I think, oh yeah, this is the thing where it frustrates taint analysis by bit copying something out of argc, and then using signal to actually pass the data around. Signal handling is pretty annoying to deal with because it's kind of that weird OS behavior. So yeah, it's great, it's modular, it's written in OCaml, and you can. So, and then, not right now, but after the talk, I will put my code onto tools.rps.ec. So if you want to have a look at the stuff I was showing earlier, you can take a look there. You will need to be on the RPA VPN. I think we're working on getting something to let off-campus people easily view that stuff, but not yet. And if you download Tigress, you can do this yourself. So, we've talked about malware, we talked about DRM, we talked about like a nice, respectable, useful, academically interesting piece of software. But there is no x86, only move. This is the infamous MOVfuscator, developed by the illustrious ZorEAX. You can check it out on GitHub at the link. And I'll just quote the README. Arithmetic, comparisons, jumps, function calls, and everything else a program needs are all performed through move operations. There's no self-modifying code. There's no transport triggered calculation, and no other form of non-move cheating. This will generate programs that are literally nothing but move. So, for example, this is prime. Okay, I don't want to read this, but it's doing some kind of formality test. This is the MOVfuscator. So we see move, and so forth. So it turns out that move is Turing complete, which is a bit frightening when you think about it, but. And if we look at the control flow graph, so again, here's is prime, and as we saw here, like, okay, there's some jumps. They go to the same place. Like, okay, there's some jumps down here, and that end. It's all good. This is the MOVfuscator. It's a line. It's quite impressive. So everything is move. Like arithmetic is move, branching is move. It uses a faulting move to go back to the top. It's completely Turing complete. Now, this might seem like a stupid joke, but one, it's not a joke. It's great, and two, it's really just an extreme form of obfuscation. It absolutely demolishes the runtime performance of your program because, as you can imagine, making everything move is quite difficult. However, it does enable you to have some very effective control flow manipulation. It's absolutely miserable to reverse engineer this. Like, you look at this, it is literally just a long string of moves. There's nothing to look at. I think I'm kind of paraphrasing him, but if you were a reverse engineer and you opened up an IDA, and it looks like this, you're just going to give up and get a new career. Speaking of that, one other amusing thing from the same fantastic person is some work on reverse engineering-based psychological warfare. So, if you opened up a program in IDA and you saw this or this, again, I think I just kind of say, that's enough for today. I'm gonna go read a book. I'm gonna do something else. I'm gonna be happy with life. I'm not gonna reverse engineer this literal skull and crossbones. But that is what he has accomplished. So if you look closely here, this is just a massive square-shaped control flow graph. We have just massive amounts of branching going all over the place, and it kind of just squeezes into the perfect shape. So again, there's something useful in here. This is kind of an attack on the reverse engineering tools themselves, and that's just what we are doing with things like overlapping basic blocks and confusing control flow. It might be more of a visual attack, but it's the same idea. It's trying to just make it very obnoxious to even see what the program is doing. Because, there's this kind of concept of security through obscurity, which I think it's a bad rap. Obscurity can provide a lot of defense. It can make it very irritating to actually even get started, or to turn an exploit into a working proof of concept and something that can actually be useful. So by taking this program and jamming it full of useless or maybe even worse, nearly useless code, because that's code you can't ignore, you get something that's very difficult to analyze and it still works, but not something you want to look at. So, kind of wrap things up here. So obfuscation is kind of a squishy topic. It's not like cryptography where you say, okay, here's my very strong hardness guarantee, and here's a proof I've broken this thing. It's a little more subjective, or even a lot more subjective. Measuring obfuscation in a meaningful way is hard. We've tried things like saying, okay, how much smaller does the program get when you optimize it, or maybe how many more branches are there? But these are all arbitrary metrics that don't really capture that fundamental idea of, I can't understand this thing, I want a new job. So it's kind of a human factors thing. But regardless, it's still powerful. De novo is annoying, isn't it? Some games are cracked before they're released, some games are cracked a few days after release, some games take a long time. And again, it's just obscurity. It's not like there's a secret key that you literally never have. The program has to still work. And that's the fundamental kind of problem for obfuscation. The program still has to work. It's not like you can't just encrypt the program and say, well, you don't have the key, you can't run it. It needs to function as a program. And so we're trying to balance this strength with this efficiency and with usability. And I think most importantly, obfuscation is kind of fun. You're writing terrible code on purpose, or shitposting for fun and profit, as I might say. So you're doing things that for any like sane program should never be done. You should never do any of these things. Like none of this makes sense. But the beauty of obfuscation is that it's kind of that's the point. It doesn't make sense. So with that, just here's the references. If you'd like to look, we will post these slides a little bit on the website. So if you'd like to go have a look. And if you're interested in the topic further, you should hit me up on the Slack. My username there is Crux. So yeah, and if there's any you guys get any questions, you can drop in the chat. I'll hang out here for a few more minutes. But otherwise, that wraps it up. So thanks for coming by. Let's see if Ninja's doing better here. Ooh, yeah, that's no good. And of course, you might think, oh, but I can clearly see this is did it. Look, all these functions called shit. But stripping the binary will destroy all of these, of course. So, you know, it gets nasty. What the medium level IO looks like. Ooh, that's good. This is Binary Ninja's medium level intermediate language. It's along with the low level intermediate language, provides you a little bit less of a straight assembly look at the program. Unfortunately, it's still not very good. Got some strings here. It's SSA. All right. Single assign. It's a real mess. And that's the objective. This is a 456 kilobyte hello world, so yeah. Anyway, if there are no questions, then I'll be ending the stream. So thanks again for coming by, and we hope to see you again next week. We'll let y'all know soon what we'll be streaming then. And also, right now we are playing Plaid CTF. So if you aren't already checking that out, I would suggest dropping by the Slack. And the Slack, if you got your RPI email, you should be able to go to. Let's just pull that up for y'all real quick. Yep. I think you go to Slack, rpsec.slack.com. Is that it? Yeah. Drop on by there. Say hello. All right. Signing off.